lecture on hemodynamics. So you might want to just check it out if you feel like it. If not, I know I did a decent enough job.
Okay.
You can wait until lab exam if you want. But there is overlap with that lab and what you're learning in lecture, is my point. Now, what is not on at all Monday's exam is what I'm about to start with you today. Something called renal clearance values. And you know what? This is not the hardest lecture. It is not. But here's why it's going to feel hard. It's going to feel complicated because you all are like this. La, 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 lecture three. That's you. And believe it or not, lecture unit 3 goes along in this lab discussion on renal clearance values. And it's a perfect application to also launch us into lecture unit 4. In unit 3, we've talked about blood flow. We've talked about how blood flows from high pressure to low. We've talked about cardiac output. We have talked about stroke volume. So we know about blood returning to and moving through the heart and back out of the heart. And these different circuits, pulmonary circuit, systemic circuit. Okay, now we're hyper-focused on one portion of the systemic circuit. Now we're focused on blood entering the kidneys and exiting. That's what we're talking about. We're talking about ways to get into the kidney and ways to get out of the kidney. Okay, how can we get into the kidney? Renal artery. Anatomy was a prereq. I'm hoping you remember your renal arteries. How can we get out of the kidney? Actually, there are 2 ways to get out of the kidney. Substances in the blood can get out of the kidney through the renal vein. Substances that are filtered by the kidney through the glomerulus, the filtration membrane, can get out of the kidney in the urine through the ureter. So that's the big concept. What is the blood going to, through, and out of the kidney? And what happens to substances that enter the kidney? How can they get out? They can come right back out in the blood, or they can leave in the urine. Those are the big concepts. There's a lot of language I'm going to be teaching you today, not expletives. Dare I say, those will be running amok next Tuesday. Anyway, depending on what happens next Tuesday, but oh my gosh, please be safe next Tuesday. I just have visions of all chaos.
Yes.
Total chaos. Of epic proportions, like dogs and cats living together, mass hysteria. Anyway.
Be kind. Everybody be kind.
Yeah.
I just, and be human.
Yeah, well,
no matter what.
Be better than human.
Yes. Yeah, that's true. That's true.
Be better than human.
Yes.
So how can we get into and out of the kidney? Lots of language. Here are the terms I'm going to be teaching you tonight. Straight definitions. So I'm going to tell you what the words mean. Then I'm going to try and show you pictures of what it would look like. If we were face to face, I would have taken about 10 minutes before class to set up a demonstration, physical demonstration, beakers. I would have had large beakers to very small beakers. And I would have added food coloring, red to represent whole blood. yellow to represent plasma, and then more of an orange color to represent urine. And I would have had these large beakers to show cardiac output, 5 liters. That's a big Erlenmeyer flask. I mean, it would be huge. I hold it like this when I bring it in the classroom. So it's nice to have those types of visuals, but we don't have those visuals. Instead, you're going to have to look at my pictures. So a lot of this that I'm doing tonight is just terminology. Don't let it bully you. Again, our main concepts. How can we enter the kidney? One way, renal artery. How can something exit the kidney? 2 ways, either coming right back out in the blood or in the urine. Well, what can get in the urine? If it gets into the urine, it must be able to be filtered. So if something comes in the urine, it has been filtered through the filtration membrane. The filtration membrane has 3 components to it. It has the simple squamous endothelium of the glomerulus, the fused basement membrane, and then it has the simple squamous epithelium of Bowman's capsule. That's the filtration membrane. So something has to be able to get through there. A lot of times students say, oh, well, what determines if something can be filtered? And they remember that the glomerulus has filtration slits. And most of you probably had an anatomy teacher saying to you, if something's small enough in the plasma, it can get through those filtration slits or pores, a lot like a colander, or a strainer that when you strain your pasta, clearly the pasta is too big to get through the holes. Okay, it's not actually size exclusion that is the primary reason why something doesn't get filtered. That is not it. Most students say it's size. It is not. Most certainly it is not. And in my very first lecture for Unit 4, I actually talk about this filtration membrane. And I talk about what limits if something gets filtered, something from the plasma entering Bowman's capsule. So here is my blood vessel carrying blood. And in the light pink part, I'm trying to show you solutes. The little black dots represent solutes. And the idea is that what I'm talking about, what gets through the filtration membrane and actually enters Bowman's capsule and the nephron, shown here in yellow. And in that first lecture, I tell you about these experiments that were very simple experiments. And what they did was they took plastic beads, microscopic plastic beads of different sizes, some very small to some very large. They even used plastic beads that were larger than albumin. And albumin is a very large protein. It's a globular protein in your plasma. You see this basement membrane with the fused basement membranes between the two. I'm going to draw it here in green. It's proteins. That basement membrane is a sheet, a layer of protein. And proteins in our body are negatively charged, aren't they? Mm-hmm. So that basement membrane that I've drawn in green is negatively charged. And what are the charges on your proteins in your blood? Still negative. So if the proteins in your blood are also negatively charged, then the number one reason why some things are not filtered, some things don't enter your nephron, like your plasma proteins, it's because of this charge repulsion. Same charges repel.
Mm-hmm.
So these scientists took these plastic beads, some of them quite large, and they gave them positive charges. And they found that beads that were much larger than albumin, that had a positive charge instead of a negative, got through the filtration membrane, ended up in the nephron. It's not size exclusion, it's charge exclusion. And in fact, there are kidney diseases where that filtration membrane becomes compromised. And when that sheet of proteins becomes compromised, has breakdown of the proteins, large plasma proteins like albumin get through. They get through. They get through the filtration slits easily. It's the membrane, the basement membrane, that repels them away. And when that happens, proteins come out in the person's urine. It shouldn't be. They should not be. And that's called proteinuria. And when you get a lot of protein coming out in your urine, it gets very frothy, sort of like when you're pouring a beer, you get a big beer head. Not good, not good. You have compromised your basement membrane. So I want you to ask you, what solutes can be filtered? And tonight I'm going to give you a short list of solutes you should keep track of. A short list, like glucose, like sodium. Sodium is a cation. It's very small. It's the most abundant electrolyte in your plasma. It definitely gets through that filtration membrane. So there are a few solutes tonight that I want you to know their fate. Their fate. What happens to them when they enter the kidney? How can they get out? What is their fate? And as I go through, I'll point out some more solutes. But right now, sodium, glucose, those are two we should start with. Okay. If it's filtered, what else happens to it? If it gets into the nephron, there's another fate we need to ask. Is it reabsorbed? Do we put it back in the blood? Is it secreted? Now, in this picture that you're seeing in front of you, you're seeing some of my solutes going from the plasma into the nephron. But some of them didn't get filtered. And now they're still in a blood vessel. And notice in this picture that later on, they get added to the filtrate. When we add to the filtrate after the glomerulus, that's called secretion. That should not be a new term for you. You should have learned about that in anatomy. So what happens? What regulates how much something is filtered and when? Don't get me wrong, size is still a factor. Those scientists used some really large beads, and even if they were positively charged, eventually they got so big they couldn't get through the filtration slits. So to some extent, size does matter. But overall, it's the permeability from the charge. If they had the same charge, they didn't get through. If they had positive charge, it's easier for those solutes to get through. Surface area is also another important thing. What does that look like? What does that mean in normal language? You have about 1 million nephrons in each kidney. You have about 1 million nephrons in each kidney. How many of you out in the audience are older than age 30? Any of you?
All right, just me.
No, we're others. So congratulations. If you are age 30, you are in early renal failure. Congratulations. Starting at age 30. Starting from age 30, for every 10 years, you have a 10% decline in the number of nephrons you have. They are dying.
Yeah.
They are dying. So if you are 40, you have had 10% decline in your renal function. If you're 50, 20%. If nothing else kills you in your life, you will eventually die of renal failure. They've actually done those studies. Why? Because starting around age 30, you're like a ticking time bomb. Those nephrons are dying. They don't grow back. And they work hard for you. Matched by gram, no other organ consumes more ATP than your kidneys. Matched by gram. They use so much ATP to move these solutes for secretion, for reabsorption. Your kidneys are exquisitely able to figure out what solutes your body should keep in you. Like sugar, it should not come out in your urine. And which solutes should come out in your urine, and how much, and when. That is a very intelligent organ, if you ask me. And yet, how does it work? How does it work? You've already learned it. I've already taught it to you. You already know how the kidneys work. You've already learned it. It was back in Unit 2. Yes, it was. It was the very first lecture I gave you in Unit 2. The very first one. Membrane transport. Get to come right back to it. It's the same. It's the same set of membrane transport. Now we're just focused on how the kidney uses it. So we're at the point in the semester where a lot of concepts are coming back. It's just, hey, this is a new organ system to apply it to. Okay. Let's start with those terms. Okay, we know, because it's Unit 3, what cardiac output is. Oh boy, some of you learned that lesson pretty hard, didn't you? I asked a question, what is stroke volume? And one of the possible answers was the amount of blood ejected from the ventricles per minute. That is not stroke volume. And a lot of you bit into that juicy apple, didn't you? I was like the witch going, here, take a bite, my sweet. Cardiac output is the amount of blood ejected from the ventricles per minute. And the right ventricle should be matched to the left. So it's 5 liters per minute. It is a flow. You learned that in Unit 3 as well. It is a flow. Hey, guess what? What leaves the heart returns to the heart under normal, healthy circumstances. That's venous return. Venous return is also a flow. And you have about 5 liters per minute of venous return. Okay, so here's this 5 liters. And if you have a liter container of soda, you would have 5 of them in front of you. How much of that blood is going to the kidneys? This is supposed to be a kidney. A poorly drawn kidney, but it's a kidney. Here's the renal artery. And here's the renal vein. How much of that cardiac output goes to, through, and out of the kidney per minute? It's about a quarter of cardiac output, roughly a quarter of cardiac output. 1/4 for cardiac output of cardiac output would be about 1,250 milliliters per minute. It will actually be closer to 1,200 milliliters per minute, and I'll explain why in just a moment. That is called renal blood flow. It is still, again, a flow. Renal blood flow is the amount of blood going to, through, and out of the kidney. Blood entering the kidney through the renal artery and exiting the kidney through the renal vein. Approximately 1,200 milliliters per minute. Do you need to know these numbers? Oh, yeah. Oh, yeah. Absolutely. Now, why is blood going to the kidney? Any guesses? Why does blood go to the kidney?
To be filtered. To be filtered.
Good. To be filtered. Okay. That's one reason. Why else? It's not meant to be a trick question.
Repulsion. Change and
so filtration, reabsorption, secretion, that's all about cleansing the blood, right?
Yes.
Is it erythropoietin, red blood cell generation?
So blood is being monitored by the kidney cells for oxygen content, true, and it would release erythropoietin. We forget that the kidneys are filled with cells that need nutrition and oxygen.
Mm-hmm.
We forget that. We just say, oh, it's the kidneys. A lot like the heart. Oh, it's the heart. We forget that the heart has its own circulation, right? The coronary vessels. Why? Why doesn't it just take nutrients and oxygen from the blood in the chambers? Because the right side of the heart then would be screwed, wouldn't it? Very little oxygen. So we forget these things. Hard-working organs are filled with cells, and they need nutrition and oxygen too. So there is some of the blood going to the kidneys for delivering oxygen and nutrition. A large part of the blood is going to the kidneys, as you all said, for processing. Let's call it processing, filtration, reabsorption, secretion. Okay, I need you to remember that. Those are the two big reasons why blood is going to the kidneys. Let's focus on the processing. Let's focus on the blood going for processing as we move forward. Well, if blood is going for processing, what part of blood could be filtered? Remember, blood is a mixture of two body fluid compartments, isn't it? It has the formed elements, like red blood cells, and then it has plasma. The formed elements part, the red blood cells being the majority of that, those aren't filtered. You should not be peeing blood. Okay? And right about now, I usually have a female that's not paying attention, and she says, wait, sometimes blood is in my urine because I'm menstruating. Anatomy was a prereq, and please understand that when blood comes out and is in your urine because you're menstruating, that came from a totally different hole and mixed with the urine coming from your urethra. So seriously, that happens. It especially happens in my class because I'm the night instructor, and I usually have a lot of people in my class that work all day and they're tired and they just have a brain fart. We all have had those. Like, oh, I can't believe, of course, I know that, you know. but it does make for kind of a good time in class. Everyone wakes up then like. So the amount of blood going to your kidneys for processing, we got renal blood flow, right? That's the amount of blood going to and through and out of the kidneys.
Uh-huh.
When we're talking about processing, we're worried about the plasma part.
Okay.
Okay, so then what's the amount of plasma going to, through, and out of the kidneys? That's called renal plasma flow.
Okay.
Okay, well, we remember that hematocrit traditionally is 45%.
Uh-huh.
So that means plasma is approximately 55%.
Uh-huh.
Can't that be a little different from person to person when they have a different hematocrit and therefore a different percentage of plasma?
Yes.
Okay, so that's why I'm saying CA stands for calculated average. Okay? So if I take approximately 55% of my renal blood flow, 55% of 1,200 milliliters will give me 660 milliliters per minute for renal plasma flow. Now, look at this picture from this slide. You can see the blood, which I will color in green here. And we have some of that plasma being filtered. And then a lot of that blood volume is going out through the efferent arterial, right? That was the efferent arterial. And then it goes to the peritubular capillaries. Yay, kidneys, we remember our anatomy. So here's my sad picture of a glomerulus. This is supposed to be the glomerulus.
Oh.
I know, glomerulus, and it's a capillary. And some textbooks refer to it as a tuft, a capillary tuft, like a whole bunch of snakes kind of writhing around each other in a nesting position. That's what it reminds me of. So here's my glomerulus. Not all of that plasma, as shown in this picture, not all of the plasma gets filtered. Can't. Think about that. If all of our plasma got filtered all at once, how would the red blood cells keep tumbling out through the efferent arterial? It'd be sludge. So it turns out we only have about 20% of this plasma, here's my calculated average, being filtered. So that number is approximately 125 milliliters per minute. That is called your glomerular filtration rate, GFR. It is about 20% of your renal plasma flow. So that's what we call your filtration fraction, that 20%. And then from that, about 123 milliliters, they are reabsorbed. And you make about 2 milliliters per minute of urine, which is dripping out of the minor and major calyxes into the renal pelvis, into your ureter, and into your bladder. And your bladder, being an amazing organ, is made of transitional epithelium and has rugae, and it can keep expanding, and it can hold a lot of urine until it's socially acceptable for you to go to the bathroom.
And I still remember you saying that it can hold a lot of urine. So at 3 in the morning, I tell myself, you can hold more. Because you said that in anatomy.
It can. But it does get to a point where it's a little uncomfortable.
Yes.
And I don't know about you, but every time I tell myself that when I'm sleeping, when I'm sleeping, and like the last couple of nights where it's cold at night and you're so warm in your covers.
No.
And then I start dreaming that I'm a kid again playing hide and seek. And I keep saying, I gotta wait, time out. I have to go to the bathroom.
You're gonna pee yourself.
And then I dream that I'm going to the bathroom as a kid, and I'm like, oh,
I better get up.
I gotta go to the bathroom. Every time.
Yep. Yeah.
Okay, so let's do it again. But keep the pictures in mind. Renal blood flow is the amount of whole blood going to, through, and out of the kidneys, entering through the renal artery, exiting through the renal vein. It is approximately 1/4 of cardiac output. So 1/4 of cardiac output would be technically 1,250 milliliters per minute. However, we have blood vessels, arteries, and arterioles that are in the kidney, and at any given moment, those are somewhat vasoconstricted. We learned about that in Unit 3. So it turns out renal blood flow is closer to 1,200 milliliters per minute. Okay? Now, I asked you, why does blood go to the kidneys? And most of you said for processing, right? That's the word we're going to use. Processing for filtration, reabsorption, secretion. And I said, well, most of the blood is going to the kidney for that reason, but some blood is going to the kidney for the sake of delivering nutrition and oxygen. So we need to distinguish the amount of blood going to the kidney for processing. And that is called effective renal blood flow. It is 90% of renal blood flow. The word of means multiplication, right? So effective renal blood flow is 90%. 90% is 0.9 of renal blood flow. Let me say that again. 90% of the blood going to the kidneys is going for the sake of processing. 10% is going to the kidneys for the sake of delivering nutrition and oxygen. When we are, rephrase. We are learning about renal clearance values. That is what we're trying to start to learn tonight. Let me tell you the importance of that. I asked how many of you are over age 30. And I said, congratulations, you're in early stage renal failure. Do you know that when you go to the doctor and they ask you to urinate in a cup and they draw blood from you, usually as well, those are like the 2 bodily fluid that they take from you, you get a report. You get your urine and blood analysis back, either mailed to you, paper format, or the doctor in real time prints it from the office as maybe they have an in-house analysis, or maybe it's electronically. You can pull that up and you can see that. And you get pages of data, don't you? Pages. You should go back and look at those things because you've learned about so much of it. You've learned about, you get on your report MCV, hematocrit, MCHC, MCH, red blood cell count, white blood cell count differential 60-30-6-3-1. And if you're out of normal range, they flag it, don't they? You get a little asterisk next to that value. They flag it. Keep looking through there. Eventually, you will see something called GFR. And that's glomerular filtration rate. That's how much your kidneys are filtering per minute. It should be close to 125 milliliters per minute. But is it? Is it? Are you over age 30? Because they're now using a sliding scale on you, my sweets. Is it? Or are you starting to slip? And then the doctor starts patting you on the head and he or she says, for your age, your kidneys are great. You're like, what the hell does that mean for my age, my kidney? Yes, sliding scale. So it might not say GFR, it might say eGFR for estimated GFR. We measure kidney function all the time, my sweets, all the time. They've done it to you. If you've had blood and urine analysis, they've done it to you. And the reason why they're analyzing your renal function is to find out if you are in renal failure. And then if they do think you're in renal failure, they need to figure out where. Carrie, that's a stupid thing to say. If it's renal failure, clearly it's the kidneys. No, no, no. Renal failure, the kidneys can fail for reasons that are not their fault. I'll put it to you this way. If the kidneys are needing the blood going to them, 90% of the blood going to them for processing, and you filter your blood about 60 times a day, by the way, that's a lot. Your kidneys are processing your entire plasma volume about 60 times a day. Hardworking organs. Your kidneys can fail. We say you're in renal failure. What if they can't do their job because they're not getting blood? What if the heart is the problem? Mm-hmm. What if the heart isn't pumping the way it should? You can go into renal failure, my sweets, but it's not the kidneys that are dysfunctional. They're not getting their, how can they do their job if they're not getting the blood? Right? That makes sense.
Yeah.
Maybe there is a plaque in the renal artery, obscuring blood flow, obstructing, I should say. How can the kidneys do their job? They can't. That's called pre-renal failure, my sweets. And then there's intrarenal failure. Well, then it is the kidney's fault. The cuboidal cells of the nephron or the squamous cells of the nephron, maybe they are failing. Maybe the nephrons are dying in significant numbers for reasons. There are lots of reasons why it could happen. Or maybe it's post-renal failure. Maybe your urine is damming all the way up. You're blocking the pipes with urine so that no more can enter. Well, how can that happen? How can you have urine damming all the way up back to the kidneys? Well, let me count the ways. You can have a renal calculus. That means a kidney stone in your ureter. Then it blocks it, and then urine can't get out. It gums up everything through the nephron all the way back to the blood vessels. You can't get fluid flowing if there's an obstruction. Maybe you're male and you have an enlarged prostate. Remember, part of a man's urethra goes through the prostate, and the prostate has hyperplasia, maybe benign hyperplasia. It occludes the urethra, and then the man cannot void, not easily. So that's post-renal failure. So we are learning these numbers. The reason why I am making you know these numbers is because these are the normal numbers. And part of your job in the next week and a half, when we finish this, part of your job is to learn how to calculate. Oh, how mean am I? I'm going to make you do calculations with your calculator, calculating someone's GFR. And then once you calculate their GFR, you're going to analyze it and tell me, is this suggestive of pre-renal, intrarenal, or post-renal failure? Arguably, it's a mean thing to do. It is. Arguably, it won't be your job, for crying out loud, as a nurse. Won't be your job. No, Your job is to get the urine and blood sample and have it sent off to the lab, and they will analyze it. They will give you the report. But your job as a nurse is to be the liaison between the doctor and the patient. And it is oftentimes the nurse that has the conversation with the patient of what the hell do those values mean? Talk to me in English. What does that mean? And if it's not the patient you're having that conversation with, sure as hell is going to be the patient's family. And let me tell you, they are worse than the patient because they are the advocates for that patient. And they're going to ask hard questions and they're going to want to know what the heck is going on. And they get mean if they feel like the nurse doesn't know what he or she is talking about. They get mean. Some of you are in the audience going, because you've witnessed that. So I'm going to teach you, it's not even, I think it's 9 equations. 9 equations. I think you can memorize 9 equations. The fun part, I think, is knowing when to use which equation. Yeah, it's like a scavenger hunt. That's what it is. You got to figure out which of those 9 to use. Oh, and then the fun keeps going because then you'll get an answer and then you take the answer and you feed it into yet another equation. It's super fun. I love those, don't you?
Oh, yeah.
It's like your math proofs. You remember those? Those were fun. No, they were not. All right. Anyway, we're going to get there. So 90% of your renal blood flow is the amount of blood going to the kidneys for the sake of being processed. And that is about 1,080 milliliters per minute. Oops. Oh. Now, I said the part of blood that we're technically able to process is the plasma. Well, depending on the person's hematocrit, plasma is about 55% of whole blood. So 55% of renal blood flow would give us renal plasma flow. And that's about 660 milliliters. I'm showing you the math down here. I'm taking the whole number 1 and I'm subtracting 0.45, which represents hematocrit of 45%. Again, that can change depending on the person's true hematocrit. And just like what we saw with whole blood, 90% of this plasma is going to the kidneys for the sake of processing. And that is effective renal plasma flow. So ERPF is, again, 90% of our original volume. In this case, it would be renal plasma flow. So 90% of 660 gives us 594 milliliters per minute. Of that 594 milliliters per minute, the forces, here's something from Unit 3, the Starling forces only allow about 20% of the plasma to be filtered. And I hope you know Starling forces, that there are 4 that are part of filtration.
Mm-hmm.
And there's also that KF factor. KF factor is permeability. Well, the glomerulus is very permeable. It's got those filtration pores. Mm-hmm. And then after that, we've got our Starling forces. We've got a capillary hydrostatic force. We have a capillary osmotic force. We have an interstitial osmotic force and an interstitial hydrostatic force. Well, in the nephrons, you only have 3 Starling forces. Why 3? What happened? Which one is gone? The one that's gone is the interstitial osmotic force. You see, there is no interstitial. There's the glomerulus, and then there's Bowman's capsule and the nephron.
Is that the number 2 one? The one with the vacuum lymph one?
Right. So instead, remember, under healthy conditions, we don't filter albumin.
Right.
So very, very little protein should get into the nephron.
Okay. And
that's the reason why that one, the nephron or the Bowman's capsule osmotic force, is gone. There should not be protein. It's negligible. So that's the one that falls out.
Okay. Okay.
So in short, because of the Starling forces and the KF factor, out of this 594 milliliters of plasma, we filter about 20% of that. And that is well, we are using the 660 for RPF here, still about 20. And that's called our filtration fraction. The question is, though, is your patient filtering that much? Do they have a GFR of 125? Or are they older and they're already on that sliding scale? Or are they young and that something has happened to them where they have greatly compromised their renal function? And I'll give you a sad example. Recently, one of our family friends, their son, who had seizures, pretty bad seizures, and pretty bad depression. And sometimes his depression got in the way of him taking his seizure medication. And unfortunately, in the middle of the night, he had a seizure. And because of the way he was laying down in bed, he suffocated to death.
Oh, God.
And devastating because he didn't get up for work, and she went in to go wake him up, and she's the one that found him. And she is grappling with severe depression now for herself because she feels tremendous guilt. And she decided that she attempted to take her own life just recently. And one of the things, there's 2 people now in my life that have tried to kill themselves by taking large, massive amounts of aspirin or Advil. And so she took a large amount of ibuprofen. Thank goodness she started vomiting it before she could really absorb a lot of it, but she did a number on her kidneys. And the reason is, and you all kind of know this story already. You know that ibuprofen is still an NSAID. It's a non-steroidal anti-inflammatory drug. And you know that NSAIDs blocks COX enzymes. And you know that COX enzymes help with the synthesis of prostaglandins. You know that. What you don't know is that the kidneys are extremely dependent on prostaglandins. And they use prostaglandins to make sure that they get adequate blood flow for their nutrition and oxygen delivery. They rely on those. And if you are overdosing on NSAIDs, if it doesn't kill you, you can do severe long-term damage to your kidneys. Why? Because you're now blocking the prostaglandins from being made. And now that 10% of blood that needs to go to the kidneys for the sake of delivering nutrients and oxygen is cut off. Those cells will die. You do know that, right? If you're not getting adequate blood flow to these hardworking cells, they are going to become hypoxic, anoxic, and then die. And she's my age. I like to think that's not exactly ancient, but she has catapulted herself into a renal failure. Her kidneys are functioning like she's 80 because of what she's done. So we measure renal clearance values all the time in a clinical setting. All the time. All the time. I'm going to teach you how to manually calculate them, knowing that that is extremely mean, and it will never be your job. Not unless you switch majors and go into the another branch of health services and get your certificate in a clinical laboratory technician, which we have that. Then it will be your job. Then you will have to calculate it. But it's not hard. And I know you can with some practice, and maybe you're not really into it tonight, but eventually you're going to have to be. And you'll come back and you'll watch this. Well, here's another something we need to calculate. And it's called filtered load. Filtered load. So GFR is a flow, and the plasma concentration of any particular substance can be measured. Yes, it can. Can't we draw blood and send it to the lab, and can't they tell us how much glucose you have in your plasma? Yeah. How much sodium you have in your plasma? They tell us how much albumin you have in your plasma. So we send the blood to the lab and they tell us the plasma concentration. All right, one of the earlier lectures we had when we first started, I asked who was my drinker in the audience. And it was a much more entertaining conversation with the Monday, Wednesday class than it was the Tuesday, Thursday class. Because I believe we were making a margarita, which was, I think, 95%
alcohol. Yeah. They were drunk in this class. Oh, I think you froze for a second. She must have had to log off and log back on. Right? Okay, everybody's not good. I always just think it's me. I'm like, I must be my internet. She's logging back on.
Can you see me and hear me now?
We can hear you.
Yes. Oh, I had a quick question before you went on.
Mm-hmm.
Do you know exactly what happens when people have nephritis?
Inflamed nephron.
It is a spectrum. And the spectrum is continuous. There is nephritic and nephrotic.
Ooh.
And so nephritic and nephrotic. And oftentimes someone is told that they have nephritis and it's actually closer to nephrotic. Nephritis is an inflammation issue. So nephritis and nephrotic oftentimes start for different reasons, but there is a convergence where they start to look the same. That's why I said it's a continuum. So with nephritis, it is an inflammation response. It also, part of the inflammation response means that you have immune cells that are part of that. And what happens is they start attaching to that basement membrane, to that filtration membrane I was telling you about. and they compromise it. So it's an immune issue for nephritis. And then for nephrotic issues, it's usually a circulatory issue. Anyway, that's the short answer. And if you ever want to be thoroughly abused with it, well, you could sign up for pathophysiology. And we definitely learn about nephritic versus nephrotic, and acute renal failure and pre-renal failure and intrarenal failure and post-renal failure. Oh, it's fun. It's fun.
Thank you. I was just curious because when I was younger, I had strep undetected and it turned into nephritis.
That is an immune response. You were sick. And so your body, your immune cells launched an inflammatory response. And when it did, your immune cells went after the antigen on the bacteria. Some of those nasty little bacteria landed on your basement membrane and your immune cells went, ah! And in their exuberance to get rid of your infection, they also did some damage to your glomerulus and filtration membrane. If you've taken micro, you have learned about the complement system. So that's what was provoked. How old were you, Hannah?
I was 4.
Okay. So youth being on your side, it's not that you can regrow those things, but here's more patho. I'll be gentle and we'll move on. When someone has an inflammatory response, there are possible outcomes. One of the outcomes for an inflammation response is not very good. It turns into a boil or a fistula. It goes into, it festers into an open wound, and then it needs medical attention. That's not what we want. Then there's, it can be resolved. And a lot of students in patho say, oh, resolution, that sounds good. We resolve the inflammatory. No, resolution means you repair that tissue, but you turn it into scar tissue. And that's not what you would want if you had nephritis. You wouldn't want to turn your filtration membrane into scar tissue. Collagen does not filter. The more appropriate outcome is restitution. And restitution means that that the inflammation process is over and the tissue reverts back to what it was. So it's not that you regrow new glomeruli and regrow more filtration membranes. The damaged parts they get repaired back to the original tissue type. And when we're talking about our kidneys and you being 4, youth is on your side. And here's hoping that very minimal long-term damage occurred to your kidneys. But I'm sure they have checked you from time to time. Yes?
I don't think so for the most part. I don't think since I had it, they've really, well, maybe, I don't know. Maybe I was just too young to know.
I bet they did a follow-up and I bet things came back with, check, she's fine. We've had restitution.
Yeah.
Thank you. I was just so curious because I've always known that happened to me, but I never knew the science behind it. Interesting.
Inflammatory response. Your body was doing too much of a good thing for you. That's what it was. Okay, so let's get back to drinking, shall we?
Sounds nice.
Yeah, so let me tell you about filtered load. So I'm going to finish slide 9 and slide 10, and then we'll stop there. We'll have our break, and then we'll switch over to exam review mode. So okay. Filtered load. Let me share my screen. I don't think I did that. No. Okay. There you all are. here is our picture of a mixed margarita. It has tequila, it has lime juice, it has triple sec, all the good stuff that the Tuesday, Thursday class should go into it. They decided Monday, Wednesday, what you all made was truly just a tequila shot. Anyway, so here's my margarita. And Sarah, I'm going to pour you a glass, okay?
Okay.
So I'm pouring you a glass, and here you go.
Thank you.
Okay. Now, the amount, the volume I poured Sarah, was it a full glass or a small amount in a glass? Here is just a small amount in this glass, and let's pretend this is our margarita mix, and let's say we've made it a strong one. Let's say it's 50% alcohol.
Okay.
Okay?
Okay.
So I can say, Sarah, let me measure how much I gave you.
Okay.
Let's say I gave Sarah 100 milliliters.
Mm-hmm.
And we know the alcohol content is 50%. So 50% of that volume is alcohol, okay? Now, I know tequila is not 100% alcohol, right? But let's just pretend. Let's just pretend just to keep the math easy.
Mm-hmm.
So the substance in the plasma concentration, think of that as our alcohol concentration. And if someone is pouring you a drink and you need to be responsible later that night, and they give you a drink, you might want to say, okay, how much is in this drink and what % of alcohol is it? Then can't you calculate how much you are totally ingesting of alcohol only?
Yes.
That's what this equation is showing you for filtered load. Think of that as alcohol load. How much alcohol am I ingesting? It's dependent on how much I pour, the volume, and for our example, the % concentration of alcohol. If you know how much you were poured, 100 milliliters, and 50% of it was alcohol, you have ingested
50 milliliters.
50 milliliters, okay? Tubular load. Okay, the proper units though, when we're talking about filtered load, we're talking about a solute, not a liquid, a solute. So the proper units will be, if GFR is milliliter per minute, and plasma concentration is milligram per milliliter, milliliters cancel out, and we're left with milligrams per minute. Okay?
Okay.
How can we get more filtered load? How can we get more tubular load? How can we get more of a substance? Tubular load means how much is getting into Bowman's capsule. Well, it's dependent on two things, GFR. GFR is held constant. Your kidneys hold a constant GFR. That is also talked about in my very first lecture for Unit 4. GFR is held relatively constant. So it doesn't really change, not drastically moment to moment. But what can change is the plasma concentration of something in our blood. That can change. Let's say I want to calculate filtered load for glucose. And let's say I have a GFR of 125, and let's say I'm a diabetic and I've just eaten a big meal and I didn't take my insulin. That is going to drastically change my plasma glucose concentration.
Mm-hmm.
And if that is going up, glucose is freely filtered. I'm going to get a lot more of that glucose inside my nephron. That's going to be a problem because glucose is reabsorbed using a facilitated means. And we're gonna reach Tmax. And now we got glucose coming out in the urine.
Yeah.
So here's what I mean by fates.
Oh, glucose.
Okay, so fates. What if you have a substance that is filtered only versus something that is filtered and somewhat reabsorbed? And reabsorbed means it's going back into the blood somewhat versus filtered and being reabsorbed 100%. That would be glucose. Glucose is freely filtered and should go back to the blood.
Should, right?
Should, assuming you don't reach Tmax, assuming your tubular load does not exceed the ability for your nephron cells to take that glucose back to the blood.
And don't get overloaded because then it's just wasted in the urine.
Correct.
And that's what we see in the diabetic patient. It just ends up in their urine.
Correct.
In the toilet.
Correct. And then there's another substance that can be filtered and then added to it that's secreted. So let's go through some of those substances. This will be my last slide and then we'll have a break. The best example of a substance that is filtered only is a substance you might not have ever heard of, and it's called inulin, not insulin, inulin. Inulin comes from like garlic, onions. It's a bulb. It's a vegetable bulb. So think garlic. I'll show you a picture of it. There.
Oh, right there.
Okay. So inulin is a polysaccharide, and it's stored basically in plants that like tubers, like garlic. They can store their sugar in those little bulbs. Onions, garlic, you get the idea.
Yeah.
All right, so inulin. Inulin, you need to know from now on, its fate is that it is filtered only. Filtered only. Not reabsorbed, not secreted. You need to know the fate because we're going to manipulate inulin for our clinical benefit. And we can manipulate it because of its fate. The only processing it can have, once it's in your blood, it can be filtered and it's going to show up in the urine. So whatever you filter, your filtered load is going to equal what you excrete. Your filtered load, that's F of S, filtered load of a substance will equal what you pee. What goes in comes out. What goes in the nephron comes out in your urine. Matchy equals. Because there is no other option. Substance B would be your electrolytes like sodium, but also you could put potassium here. It depends. They are freely filtered and you can reabsorb them. How much? Depends on how much your body needs. Are you eating a high sodium diet? Then you're probably not going to reabsorb as much sodium and you'll have more of it come out in your urine. Are you on a high potassium diet? Then you probably aren't going to reabsorb as much potassium and you'll have more coming out in your urine. So partial, we'll think variable. So let's just say you do filter, but you reabsorb some, not all. Then you're going to have what shows up in your urine, that's excretion, will be less than what you filtered. Why? Because you reabsorbed some. You put it back in the blood, you kept it. So we have more going in the nephron than coming out in the urine. Substance C, glucose, we talked about that. Under normal healthy conditions, what you filter, you reabsorb, and you should not see anything coming out in the urine for glucose, not under normal healthy circumstances. And then substance D is a substance that is filtered, and whatever didn't get filtered gets 100% secreted. So all the blood exiting through the renal vein is cleansed of that substance, cleared of that substance, and it's all coming out in the urine. So you get more coming out of the urine than what you calculated for filtered load. Sometimes students say to me, Kara, how does that look if we go back to our margarita analysis, if we use our margarita analogy? So my margarita analogy, Kara, you poured me 100 milliliters. It was 50% alcohol. So it was 50 milliliters of alcohol that I drank. What does it look like then if I use that margarita? How do I get more out of my urine than what I filtered in, than what I consumed? And this is my analogy. While you weren't looking, someone topped off your drink with just pure tequila and they added to you without you knowing. So that's the best way I can think of an analogy for that, which is pretty still lame, but it's better than nothing. Now, a substance that you're going to learn about is something called PAH, and it stands for para-aminohippuric acid.
Oh.
And I know, here, I'm getting to the slide where I write it out. Here.
Okay.
Para-aminohippuric acid, PAH.
Acid.
Okay. And when I see you, again, to continue this lab, which will be next Wednesday, we will finish this next Wednesday. Hopefully we won't be in chaos of epic proportions. I will finish this and we will start working in our lab manual calculating renal clearance values. So by Wednesday, you should be in a better state of mind, I hope. And we'll actually do math calculations then. Why don't you take, please, a 10-minute break? And I'm going to pull up my other computer and get set up for a Lecture 3 exam review, and also address the cardiac cycle beast picture that a few of you have asked me questions about. So I'll address that. And then when I'm finished, I will answer your questions if you have any. So go take a 10-minute break and I will see you shortly. I'll get set up.
Thank you.
Is everyone back? Okay. What's up with the witch hat, right? Well,
I love it.
If we were together face to face, this would have been our last day together before your lecture 3 exam because it got moved. And it would have been our last time together before Halloween. And Halloween is my absolute favorite, absolute favorite. Why is it my absolute favorite? Because never do you ever have the argument of where are we spending Halloween, your family or my family. You never argue over that. It's bliss. Starting Thanksgiving and Christmas, the fighting begins of where are we spending the holidays, your family or my family. Halloween, no one cares. It's my favorite. So I would have come dressed up in costume today if we were face to face. And I would have given you your extra credit would have been, you would have gotten extra credit if you showed up in costume, and it had to be a legitimate costume. We vote. Some of you showing up in scrubs saying, look, I'm a nurse. Not when you go dressed in scrubs to work every day. So we would vote. One of the best costumes I've ever seen, and I have pictures of it somewhere. I had a student show up and she was wearing a blonde wig and she was all dressed up in heels and stuff like that. And I went, what are you supposed to be? And she stands up in front of the class and because I'm like, what are you? Because I can't tell, this is not legitimate. All you are is wearing a blonde wig. She goes, I'm Kara. And then as soon as she said that, the class looked at her and went, oh yeah. And she turned around and she marked with eyeliner on her calves, on her gastrocnemius. And she goes, look, I even have Kara legs. And she wrote Kara legs on her legs. It was cute. Anyway, that one was cute. And then another student in that class, he came into class late. And I called him out. He had a good personality. So I was like, what are you doing? You're late again. What are you doing? And he's like, I had to get dressed in my costume. I said, well, where is it? I don't see, where is your costume? And he comes up closer to me and he has tape. He has tape going down his belly in an arrow. Okay, and an arrow pointing down here.
Nice.
And then down here, he has this big plus sign, right? Big plus sign. So he has an arrow, big plus sign down here. And I said, what are you supposed, what is that? What? He's like, I'm a vector. He said, I'm AVF. And I went, you get the most points for that because that was clever. Anyway, so here I am in my costume, and I would have been given, I would have brought in food for you all. We would have had a good time, food and candy, and it would have been a surprise. You'd be like, oh, we're having a party? Yeah. And we would have a parade. We'd walk through the building. It's super fun. I know I'm corny. So
look at everybody smiling. We're also happy right now just thinking about it. Damn it.
It is
Ethan's
fun.
smiling. Look how happy Ethan is right now too. Gosh dang it.
So here's my Halloween poem for you, and it's your review. Here's your Halloween poem, and it's your review. And you don't have to scramble and write this down. I will post it on the announcements page, okay? So here it is. This took a long time. And I'm not the best poem writer, but here we go. It's a long one. I'm a witch, remember. So this is my spell. I've tried and tried to capture you. What more can one mere spirit do? Listen hard, all you lads and ladies. This unit's test is a test from Hades. My brew and potion boils and bubbles, poison darts, red poison apples, cafe casita non caffeima. You should know all causes of edema. Dearly departed in rows of stone, specialized contractile cells aren't alone. Take care, beware, heed my warning. Study their action potentials now till morning. Annula campana on St. James Eve, a dash of orange and ambergris. Incantate Miss Mary Mac. Mac? Ohm's law is back. Some say to run or you'll get burned. I would know my Venous Return. It's the biggest influence on CO. Don't rely on eeny, meeny, miny, or mo. My class filter will entrance you. It will pomp and circumstance you. Onisin, Otilin, amulet, fetal blood flow may get you yet. For whom the bell tolls, you'll never know. It's hard to say when it's your time to go. As you draw in your sweet final breath, knowing cardiac drugs can save you from death. With spiders 10 fray lockers blue, eye of newt will stew and brew. PDA and Tetralogy of Flow. This is corny. Miss Lucy's in heaven and the steamboat's below. For me to stop haunting, you'll have to petition, for I'm one spooktacular apparition. Baroreceptors can save you from dying. They even change upon standing from lying. My love potion boils and bubbles, poof, goes all your toil and troubles. Blueberry wine and gladii, resistance changes most with radii. Enchantra, Endora, Tabitha, Esmeralda, Clara, Hagatha. Stenosis, prolapse, what sounds will there be during ventricular systole or diastole? Coriander, vervain, and ginger root, Damiana, henbane, and badger's foot. Incantation with magical feast. Be sure to master questions on the beast. Now you see me, now you don't. Wanting you to drop, I surely won't. Hansel and Gretel escaped my doom. I'll snatch you next. Our exam is soon. That's my poem. It's so much better during Halloween. I don't know how to turn that into Here Comes Peter Cottontail for a spring semester. I have to figure that out. I don't know how to do that. But anyway, so I will post that on the announcements page. And now some more particulars to help you with that review. Excuse me, where's my Kleenex? Here it is. All right. So I mentioned in the poem that you should know your cardiac drugs. Absolutely. Matching, very similar to what you saw in Unit 2 with matching your drugs to their outcomes. Some of them are old friends from Unit 2. Atropine, pilocarpine, epinephrine, propanolol, and the newbie, digitalis. So know your drugs. Be able to match them with descriptions. Again, very similar to what you've seen in your homework packet, what you've seen in Unit 2. At this point in the semester, there really shouldn't be any surprises. I'm looking through the homework packet to see where there is the best example of that. Yeah. excuse me. Yeah, so there are quite a few examples of in Unit 3 of your different drugs and how best to match them. So that's good, that's there. In fact, there are examples in your homework packet that has atropine, propranolol, epinephrine, pilocarpine, digitalis, and there's also curare, just as a little throwback from Unit 2. So again, there will be 100 possible points. Remember, your extra credit comes from showing me your evidence of voting or sending me a paragraph if you cannot vote, telling me what you care about, or maybe someone you're voting for locally. You don't have to tell me who you're voting for, but if you do, your paragraph tells me why. No judgment. I like to read other people's perspectives. It gives me new insight. No judgment, but do send it to me before your exam. In your homework packet, there are examples of how we can change total peripheral resistance. That is an abbreviation I use, TPR. Please remember that means total peripheral resistance. And in the lecture for hemodynamics, you learned that we cannot directly measure total peripheral resistance. Instead, we use Poissonier's law, and we know factors that influence resistance. Things like viscosity, blood vessel length, and as I said in my poem, the most important is radius to the 4th power. Small changes in radius can lead to big changes in resistance. And here is another cautionary tale. When the question is asking about blood flow through a vessel, if the radius decreases, leading to that vessel, then blood flow will decrease because resistance went up. It is a different concept when you apply this change in radius when you are talking about a person who's in shock. So I talk about changes in radius from the perspective of, is it blood going through a vessel? Just think about blood through this vessel versus think about someone who's in shock. And what is the best thing for the body to try and restore blood pressure? The best way to restore blood pressure in someone who's in shock is to have vasoconstriction. Put the pressure back on the blood. And that was something that I tried to point out quite a bit in that shock lecture for the cardiovascular system PowerPoint, the problems, cardiovascular issues, where you learned about stenotic and prolapsed valves. Towards the end, you learned about shock. Shock, compensation for shock was talked about. That is systemic change, total peripheral resistance throughout the body. That's different than the line of questioning asking you, if the radius through this vessel decreases, what will happen to the flow? It's going to decrease. So systemically, whole organism versus individual blood vessel. And in the test questions, I actually say, for example, consider the brachial artery. That is a vessel. Do not think systemically. Again, in your homework packet, there are problems or questions that give you examples to these types of questions. Pay attention to your homework packet is always what I'm going to say. In the poem, I told you to know the action potentials for your specialized versus contractile cells. They look very different. One has a pre-potential, one has a stable resting membrane potential. One has 5 phases numbered 0 through 4. One has autorhythmicity. What causes the autorhythmicity? In the lecture, I said that it comes down to potassium and sodium permeability changes, that the autorhythmicity is mostly attributed to these days to less leaky potassium channels. If there is less potassium leaking out of the cell, that means we have more positive charges trapped, but also leaky sodium channels. So that means more sodium coming in. That also means more positive charges coming in. In this unit, we also have page. We have sympathetic and parasympathetic tones from unit 2. That came with us. So you learned about chronotropy and inotropy. And there were, in the cardiac cycle especially, there were drugs, there were symbols. Remember, chronotropy always comes first in the parentheses, and inotropy comes next. And with the drugs, I told you how some drugs can lead to negative chronotropy, positive inotropy. For example, that was digitalis. Atropine. Well, atropine blocks muscarinic acetylcholine receptors. So if it blocks muscarinic acetylcholine receptors, it's going to block parasympathetic. And that means indirectly, it gives more control to sympathetic. So what was the nomenclature I told you for atropine?
++.
Correct. So be ready to match those types of descriptions to those drugs. And also understand fundamentally which of those drugs or systems, remember, vagus nerve is part of the parasympathetic division. We even did a PhysioX that showed that again. Understand what can slow down heart rate and what can increase heart rate. Frank-Starling mechanism is on here. It is a length tension relationship. It states within reason, within limits, more stretching of the cardiocytes can lead to more opportunity for power stroking within limits. It's an intrinsic mechanism to ensure if more blood returns to the heart on the next beat, more blood leaves. So we don't get damming up of blood.
More in, more out.
More in, more out. The slingshot. Not really sure, but I think in the video, I think, because usually when I am face-to-face, the example I use is I pretend I have a slingshot in my hand. And I ask the person in front of me, here, hold my slingshot. And they hold it, they pretend they are. And then I take the pouch and I'm holding it right in front of their face. And I pretend there's a rock and I say, now, how hard, if I pull the pouch this far back, how hard will the rock hit the person in the face? And students get the idea that that's a length tension. If I don't pull the pouch as far back, the rock isn't going to launch as much and it's not going to hurt the person. And it's usually funny because whoever's holding the slingshot, as soon as they realize, even though it's pretend, that the rock is coming at their face, they usually go like this. They hold it off to the side. And then I say, oh, so now the person behind you is going to get the rock to the face. Good job. In the video, you heard me a couple of times, blood flows from high pressure to low, In order for blood to move from one vessel to the next, the downstream vessel has to have lower pressure than the upstream vessel. So the aorta has to have higher pressure than a muscular artery. And a muscular artery has to have higher pressure than an arterial. And the arterial has to have higher pressure than the capillary. And the capillary has higher pressure than the venule. And the venule has higher pressure than the vein. And the vein has higher pressure than the vena cava. And the vena cava have higher pressure than the right atrium, which you learned on Monday. The pressure in the right atrium is known as central venous pressure, and it should be 0. But can it change?
Yes.
It can get worse, which means positive number, and then you don't have as much venous return. Or it can get better. It can get negative number, and that happens when we exercise. In your video, you learned about active hyperemia and reactive hyperemia. They both have similar outcomes, which means blood flow increased, either increased more above baseline or restored back toward baseline. But they start for very different reasons. In active hyperemia, I showed you on a couple of slides, and I used red stars, which of the chemicals can lead to vasodilation of the upstream arterial and lead to more blood flow, right? I showed you that. Things like carbon dioxide building up. And the reverse of that is reduced oxygen. Potassium. I think I made a comment in the video of where we have more potassium, we have more acids, so a lower pH. And when will cells have a lower pH? When they're more metabolically active, right? We make more acids as a result. So do know your chemical signals for active hyperemia. There's matching of shock terms to their descriptions. And I'll remind you that when I started telling you about shock in that video, I said that the term for generalized inadequate blood flow through the body is called circulatory shock. And then how can we get circulatory shock? I said there were 3 ways. It's either a heart problem, a blood vessel problem, or a blood volume problem. Those were the 3 ways. So I talked about hypovolemic shock. I talked about vascular issues like neurogenic shock, for example, anaphylactic shock. And then I talked to you about cardiac shock, cardiogenic shock. So be ready to match those descriptions to the correct terms. Same thing for fetal blood flow and fetal blood flow considerations. What is a patent ductus arteriosus? How is a patent ductus arteriosus changing the direction of the shunt versus when that baby was a fetus? So ductus arteriosus in a fetus is a certain direction shunt. And when that fetus is born, if there is still a patent ductus arteriosus, it's a different direction, isn't it?
Yes.
Mm-hmm. And then tetralogy of flow. Also be able to tell me what kind of shunt it is, what kind of, where is the problem? Tetralogy of flow is true classic blue baby syndrome. And I tried very hard to say that with patent ductus arteriosus, there is a portion of the baby that will be cyanotic, but the entire infant will not be. It is not considered blue baby syndrome. Classic blue baby, the whole baby is blue and cyanotic. That's Tetralogy of Flow. Please review your fetal structures. Anatomy is a prereq. It's Halloween, trick or treat. It's not on me. It's not a trick if you don't remember your fetal structures. Sometimes I just make stuff up and I try and make it sound so ridiculous that it's almost embarrassing when a student picks that as an answer. And this is the logic they tell me. I couldn't remember. I've never heard of that before, so I assumed you knew more than me, so that's why I picked that structure. Like, what the heck? It sounds awful. It doesn't even exist. I made it up. Like, well, I thought you were trying to trick us. I'm like, well, I was trying to, like, if it
give you an easy no.
If it could talk, it'd be like, don't pick me. There is no such thing. Okay. And just so we're clear, the ductus arteriosus is a vessel. It is a vessel. The ductus venosus is a vessel. Foramen ovale is not a blood vessel. It's a hole in the heart. It is not a vessel.
Okay.
So I even, I try and underline words or bold or highlight them for a reason. So if it says vessel, make sure you pick something that is a vessel. There are questions regarding KF going up, KF going down, and your Starling forces.
Those darn Starling forces.
And again, there are examples in your homework packet, but in the lecture, I also state, depending on the edition for Guyton and Hall you are using, you should look at that page because Guyton and Hall also tells us some other reasons why a person can have edema. Okay. And if you look at that list, you'll see things like vitamin C deficiency. That is so random. That is not on there. But there are some in that list where you should look at that and go, Kara actually kind of talked about this. Things like if your veins, if the valves in your veins fail, right? I talked about venous valves. So if those fail and you don't get blood returning to your heart as well, which Starling force is compromised now? In there, it also talks about temperature. Temperature. Well, temperature, if body temperature goes up, we get vasodilation, right? So what would that do to a capillary bed? And remember, these Starling forces are talking about a capillary bed. Capillary bed. Here's why I'm making a big deal about that. Remember when I warned you about blood vessel versus systemic?
Mm-hmm.
Okay, so let's say someone's in anaphylactic shock. What happens?
The blood pressure goes down.
Okay, so Sarah,
okay,
you just identified blood pressure goes down. That's a systemic response, isn't it?
Okay, yes.
Okay, but why does it go down?
This is something I highlighted that I have to review towards the end of that lecture, so don't pick on me right now.
That's fair. That's fair. Does anybody want to help Sarah out?
Help me out, guys, come on.
Why during anaphylactic shock does the person's systemic blood pressure go down?
Is it because there's dilation, like venous dilation?
There is overall vasodilation, correct? Why? Keep going. Come on, keep
Because you release histamine.
Good. So
Nice.
it's an immune response, and
Okay.
there's histamine released profoundly through the body, profoundly. So all the blood vessels lighten up, they vasodilate. Okay, the person's blood pressure drops dangerously low. Where's their blood? When all these blood vessels vasodilate, where does the blood go? Where is it? It pools.
In
Where's
the
it
veins
pool?
then.
It's in the capillaries.
Oh, it's
And
just
so
hanging out then?
it's just pooling. There's nowhere for it to go. There's no pressure.
Wow, it's not being pushed. Okay.
Right? So it pools in the capillaries. And so this is where in the Starling forces part, when you heard about histamine, because I talked about it, I said this one has two answers. I said it changes KF and it causes vasodilation of the upstream arteriole. Okay, so when this happens all throughout the body, all that blood pools in the capillaries, my sweets. And because the KF factor has increased, guess what? Then some of their blood plasma oozes out into their interstitial space, and that makes their low blood pressure even worse, doesn't it?
Yes.
Yeah. So that one is a tricky one because histamine can be a local to lead to more blood flow locally, or it could be a systemic massive response that we see in an anaphylactic response.
So this would be an increased KF. I get that. And an increase with this next Starling force, would that be an increase osmotic colloid? No, I'm sorry. What is?
It'd be an increased capillary hydrostatic pressure.
It's always the increased capillary hydrostatic. That one is always up there on all those things. Okay.
But that's the one that students miss the most with histamine because they think, oh, histamine.
It's high blood pressure.
Histamine anaphylactic would be low blood pressure. And then
because they're having low blood pressure.
They have low systemic pressure, but all the blood is pooling in the capillaries. So the capillary hydrostatic pressure is high.
And it's also coming out because also the pores got kind of big too, and it's coming out.
Correct.
Okay.
Yep.
Oh, those Starling forces, those are just a little intense for my brain.
Hey, you know what? Here's the
okay. We got it. Everybody's got it.
Here's the happy news. Hey,
2 questions.
You're gonna spend so much time on those that you're happy to know that they come back in lecture unit 4.
Oh my, happy day. Happy flipping day.
Well, don't you hate learning something just for all of 5 points on an exam? Doesn't it make you happy that your efforts will continue to be rewarded in unit 4?
Yes, because you know what happens after the test? Once you've done the test, you actually understand the stuff. Once you've submitted and you're done with the stress of the test, and you're like, oh, I actually get it now that I'm done stressed about the test. But
yeah. So it comes back in unit 4.
It's wonderful.
Prolapsed and stenotic valves, matching them. When you hear heart sounds, would it be during ventricular systole or ventricular diastole? Students typically do very well on that section. Again, it's matching. In the lecture, I went through the left side of the heart and told you if it's a stenotic bicuspid or prolapse bicuspid, stenotic aortic semilunar valve or prolapse. I said, now you should be able to do the same thing with the valves on the right side of the heart. And I say, the only thing that changes are the following: the names of the valves and where you get the edema. As far as when you would hear the sounds, it's the same time, ventricular systole or diastole, as what I told you on the left side of the heart. So the names of the valves and where the edema, remember, if it's a right-sided heart problem, where do we see the edema?
Isn't it? Well, on the left, it's usually pulmonary, isn't it?
So if it's right side, where do we see the edema?
Systemic.
Good. Good, good, good. Okay, there will be a word spell. You will be asked, you will have about 9 statements for muscle contraction. And your answer choices will be skeletal muscle, cardiac muscle, or both. For example, this muscle requires calcium for contraction. Both do. Of course they do. Muscles are striated.
Both.
Yeah. So you're going to have to pick, does this apply only to skeletal muscle, or does it apply only to cardiac muscle, or is this a property shared by both? Yeah. And this, you can get some information regarding this if you watch the Specialized and Contractile Cells lecture. I do some comparison there. And then I believe another set of comparison notes were done in the cardiac cycle lecture as well. And then of course, you can always go back to lecture unit 2 if you need to, and look at your homework packet with skeletal muscle contraction just to review that if you need to. Which brings me now, yes, there will be a relationship. No, we don't tell you what it is in advance. Okay, so this brings me now to the cardiac cycle homework packet part. And before I share my screen, are there any questions that you have for me before I move on to this last part? Okay, then I am going to pull up that part of the homework packet so we can see this. There you are. So this is your homework packet that I have.
I need to submit mine tonight.
Let me get to my picture. Why am I doing that? And when I can use this. There we go. Okay.
Oh, the beautiful picture.
This is the exact same picture you can expect on your exam, the exact same picture.
Okay.
And so notice that we give you ventricular volume. What is missing are the heart sounds and the force, the tension curve, and the EKG. When we were face-to-face, sometimes we said to the students, you need to draw in the remaining lines, and it was worth 2 points. Obviously, we don't do that because everything is on Canvas, and there really isn't an opportunity for you to draw on your computer screen. So we give you this picture, and you can have a scratch paper, of course. And if you and you can have on your scratch paper, you can print that picture because that's the same picture we're going to give you on your exam. So if it helps you to have that picture in front of you, this homework picture, you can. And then you can use it to answer the questions. So I am going to go through these homework packet questions just to give you an idea, to make sure you understand how we expect you to answer for if it says instant versus interval. Let me get back to physiology and not anatomy. There we go. Okay. All right. So draw. Okay. So my stylus is not letting me draw right now. That's fine. Instant marking atrial depolarization. Well, let's say you don't have your picture in front of you, but you're looking at this picture on your test. I know atrial depolarization will lead to atrial contraction.
Mm-hmm.
And when the atria contract, I am going to get that last 20% of blood being ejected.
Mm-hmm.
And when I practiced on my EKG, my beast, I know atrial depolarization was the P wave. And there is a letter that goes across, I should say the P wave goes across a certain letter.
Mm-hmm.
I'm going to pull up my picture just for the interest of time. My PowerPoint picture. And it should be letter E. So I need to explain.
Look at everybody nodding. Good job, guys.
What, everyone agrees with me? It's letter E?
Everybody was nodding, or at least, yeah. We're like, E. Yeah, we know this beast. We tamed it. Uh-huh. Everybody's smiling.
Okay, good. That makes me happy.
I mean, test night, I might be like, oh shit, what is it? I don't remember. And like this, you know, on proctorio and we're all cussing in the camera. I give myself a migraine.
Okay, so in your homework packet, you'll notice that you have only 5 letters, A, B, C, D, and E. And yet on the beast picture, which I'm about to share with you, there are more lines. Well, back in the day when we took exams face-to-face, you used a Scantron form, and the Scantron form only goes up to letter E. Proctorio allows me to go up to letter Z.
No, thank you.
I know. So here's how they are labeled in your homework packet, my sweets. You see those 2 close together parallel lines are labeled A and B, C and D, and then this line is skipped,
Mm-hmm.
and then this one is letter E, and then it starts over again. Mm-hmm. And then over here it would be letter E again. So in your homework packet, your picture kind of picks up here, right?
Right.
Sort of like that. And again, you're given the volume lines. You're given the volume, which is shown here in blue. That is in your homework packet. And you'll notice down here, I'll highlight it in green, on the EKG, the P wave spans across the line for letter E. And so if you have your homework picture in front of you when you're taking your test, you can fill it in and you can remind yourself that it is the instant marking atrial depolarization would be the P wave, and that goes across line E. Instant at which first heart sound begins. Well, the first heart sound begins when we have the ventricles starting to contract. The blood is pushed up superiorly and closes the AV valves. No blood is coming in, no blood is leaving, and the blood in the ventricles at that time is swirling around in the ventricles with nowhere to go. So that instant that marks the beginning of heart sound 1 would be letter A. Did everyone mark that for their homework?
Yeah.
Instant when AV valves open. Now, I know you all are looking at the PowerPoint, but I have already switched back over to my Word document. I don't think you all have jumped with me, right? You're still looking at my PowerPoint, are you not?
You still have the B step for us.
Right. So when I jump from PowerPoint to Word document, you all don't go with me.
Now we have your face.
Yes. And now I am sharing my Word document again. Okay. So number 88, instant when AV valves open. Now, okay, I don't have my PowerPoint in front of me. I'm going to reason myself through this. I can see it in my mind. When the AV valves open, that means ventricular volume starts to go up. I'm starting to fill. Well, volume is shown here on this test picture. So where is the volume starting to go up? Letter D. That's where the volume in the ventricles starts to go up. So that would be the instant when AV valves are open. And let me caution you, AV valve stands for atrioventricular valve.
Right.
Be careful on that cardiac cycle PowerPoint. Notice on the PowerPoint, they have an arrow pointing to where the aortic valve closes. And when students keep practicing the beast and they are writing aortic valve closes, they start abbreviating.
Yeah.
And guess how they abbreviate then?
AV inset.
And then that's the wrong valve, my
Right.
friends. That's the wrong valve. So I would put ASL for aortic semilunar valve if you're going to abbreviate in practice, but
just write out aortic.
Or write out aortic, yes. Instant at which ventricular, and that should read pressure first exceeds aortic pressure. Now here's another caution. In the heat of the moment during an exam, students misread the word aortic versus atrial. Slow down. If the ventricles now have a pressure that exceeds aortic pressure, specifically if the left ventricle has a pressure higher than aortic, blood flows from high pressure to low, and this means you're going to get ejection. So now that tells me the volume in the ventricles is going down. So when is the moment that happens? Letter B, as in boy. Interval requires more than one letter. Interval that marks the most rapid drop in ventricular pressure. Well, that tells me the ventricles are relaxing. And where is the steepest drop in that pressure? It would be between letters C and D. So that's my interval, C and D. 91, instant when atrial pressure exceeds ventricular. Now my atria have a higher pressure than my ventricles. When is that going to happen? What will happen, I should say? That means the AV valves open. It means the ventricles are going to start filling with blood. We've already had this problem. That's letter D, as in dog. Interval of ventricular emptying. Where is the volume going down before it flatlines? Where are we emptying? Between letter B and C. B as in boy and C as in cat. Interval of isovolumic contraction. A, B. The ventricles are starting to contract. The pressure curve is going up between A and B, but the volume is staying the same. Why? All 4 valves are still closed in between those 2 letters. Interval during which you would hear a murmur associated with mitral valve regurgitation. Okay, mitral valve, which side of the heart is that on? Left. It is the left AV valve. When would I hear turbulent flow from the mitral valve regurgitating, prolapsed? During ventricular systole. So when the ventricles are contracting. And when are they having this maximum force of contraction? Between letters B and C. That's when you would hear the mitral valve regurgitation. Okay, that marks the end of my review. Do you have questions for me?
I think that was a good review.
Okay, good. I think so too. I will post my little Halloween poem. No, it's corny, so corny. I will post it. Is there even Halloween this year?
I don't know. I've been eating candy, so I think so. Not that much though. Not that